Welcome back, everybody. Let's continue our exploration of the ecosystem. So again, what is tough with this part is that probably half of you are bored and already knew these things, and the other half might see it for the first time. So I'm really trying to give a good, to give basically food for thought for everybody here. Just to get a feeling. So here, for example, in the lecture hall, for whom all of that you already knew that. Okay, who didn't know these things? That's perfect. Okay, so that's half-half, exactly. Awesome. So we have this session. So we have the client interacting with the server. Again, in this course, the client is your laptop, but in a company, that would be the application server. And so when I talk about this module right here, so the module, the module right here is the software that you use to basically use in conjunction with a PostgreSQL. So now I'm going to show you a bit more details about that. Let me start with the first one because this is the one you know. This is where you're basically typing queries on your screen and you see the answers on your screen, right? So this can be a SQL shell in the command line for the geeks, but it can also be a Jupyter notebook, where that's how you have in the exercises. So this is the generic user-facing SQL interface. But then this is when things get serious and you actually have a production environment in a company. Then you stop doing that, obviously. And instead, what you do is that you embed SQL in a host language. That host language could be Java, PHP, C++, Python, R. So there's many, many different languages. But that host language is not a query language. It's really a more generic programming language. And that programming language interacts with SQL. When I say interact with SQL, I mean it creates SQL queries on the fly and processes the answers of the SQL queries, right? So the term host language, you should remember, a host language, right? I'll show you a few examples of that. And finally, we have other ways of interacting with the data. These are called table APIs or data frame APIs. Whoever heard of data frame APIs? Who heard of pandas and NumPy? Okay, yeah, so this is it. So when you use pandas, that's typically a data frame API or a table API, which is yet another way of interacting with a database server. In that case, you kind of bypass SQL because you use an API instead of writing an actual SQL query. So it's kind of an alternative language. Quick question. Who knows what API means? Just raise your hand. Who doesn't know what API means? Okay. So API means application programming interface. Application programming interface. An API is basically an interface between a computer and a computer. So what is an interface between humans and humans? That's language. I speak English with you, you speak back English to me, right? Then you can use some specific languages like mathematics, some specific vocabulary when there are people in your field, but we have this way of communicating. An API is the same thing, but between computers. And so what happens is that when a computer talks with a computer, it's basically going to call some functions and get some responses. But the way the functions are called follows some structure and some contracts, right? Let me give you an example of an API. Imagine I have a calendar application. My API could have functions that create a new entry in the calendar, like add a meeting on that day at that time. Another function in my API could be delete that entry. Another function could be send out the emails to all the participants to that meeting and so on. That is an example of an API. But the difference with the actual calendar app that you have on your phone, so when you have the calendar app on your phone, you just click on it, right? You click on it, you enter things and so on as a human. But the difference is that an API will not be you clicking on it and interacting with it. It will be a computer program making function calls from the calendar. And this is what we call an API, right? It's a program talking to a program. For whom is that clear? Right. What I found very funny is that somehow, since I think it's been 5 or 10 years, API seems to have become a buzzword in the investment world somehow, you know, just like blockchain and the cloud and so on. And so I heard some business people, like investors, like, oh, like API, we want APIs, you know, and that was actually very funny because API is actually quite an old world in computer science, but apparently it's becoming a big deal now and I think the reason it is becoming a big deal is really with this idea that computers talk with computers in the automation. You know, maybe you heard of smart contracts, like on the Ethereum blockchain. It's a little bit going in that direction, like computers to computers. All right, so that's what an API is. I just wanted to make sure that it's clear to everybody. Okay, now we have a problem, and the problem has to do with point 2 here, embedding SQL in a host language. Because something happens when we try to do that. And what happens is that the way SQL works is completely different from the way a host language works, like Java or C++ or Python. They don't even speak the same language. It's like two people meeting who don't speak the same language. Because in SQL, the words we use they should be familiar to you now because we've been doing that for weeks. Values, tables, rows, columns, attributes, projection, selection, join, sort, grouping. So all of that, now you're familiar with that. That is the world of SQL and the relational model and the relational algebra. But when you talk to a Java programmer or a PHP, who knows Java? Who knows Python? Who knows C++? Okay, so you're quite familiar with these languages. Probably when you use these languages, you never ever heard words like selection, projection, grouping. That doesn't really exist there. Instead, what you use is a string, an integer, a pointer, an object, an array, an assignment, a loop, a branch, like, you know, and all of this vocabulary. This is what we call an impedance mismatch. An impedance mismatch actually comes from the electrical engineering world. It's when you basically connect microphones and loudspeakers, and you know when you have this whole what you're doing basically outside for ETH Day, and you have an impedance mismatch when you're basically plugging a cable with something that's not appropriate in terms of what's called an impedance. And we use that word impedance mismatch also in the world of databases to when there are situations like this, that we have two completely different worlds. So now what we are trying to do is basically, we're asking a language like Java that speaks this vocabulary, that basically builds SQL queries that speak this vocabulary and return also that vocabulary, but then you have to make it back into Java objects or Python, Dix, and so on and so on. So because of that impedance mismatch, an enormous amount of engineering work has been done in the past, I would say, 30 years. Let me say 30 years. So in the past 30 years, I was just looking at the origin. So object-oriented programming is kind of, let's say, 30 plus years old. Let's say Java, 30 plus, C++ maybe a bit more. But basically, there's been a whole area of research, R&D in companies and software products, and also in academia, whose job was to try to glue that together, right? And you might have heard of object-oriented databases, trying to basically combine object orientation with databases. And so today, you have a lot of frameworks that kind of connects an object-oriented programming language to a SQL database, making it look like they are not actually interacting with the database, but just with another object-oriented language, right? So you basically wrap all the relational tables and the query in something that looks like Java objects, right? And so you can define all kinds of mapping. So basically, when you have a SQL schema with a specific number of columns and a specific number of data types, what you will do is basically create a Java class, the fields of which are the same as the table columns, and the data types kind of the same as the Postgres data types of the columns, right? For whom does that make sense, right? And I said kind of because it's not exactly, because if you look at the Java type system and the Postgres SQL type system, it's not the same type exactly. So there has to be a bit of imprecision and, you know, again, impedance mismatch between the two. So basically, what I'm saying is, it's difficult. And because it's difficult, the slides that I'm about to show to you are very ugly. So I have to warn you of that in advance. And I'm not expecting you to know all these things. This is just to give you a taste of what it looks like. So the idea is that from a programming language perspective, now you have your imperative hat, right? So you prepare what's called a statement. You bind some parameters, maybe those that the user on the website entered, like their search. You execute the statement, means you ship the SQL query to PostgreSQL internally, and then you process the results. So there is something called the Java Database Connectivity, JDBC, that is some way of connecting to the SQL database. And then what you have is you have some language extensions that basically put SQL inside your language. I warned you, right? This is very hard to parse and ugly, but this is what it looks like. You basically have a host language. In that case, I took C, right? C as a host language, where this is all C, right? This is a function that doesn't return anything, right? That is declared in the curly brackets. This also is C. But then what you do is that you extend C with this uppercase, because everybody thinks like uppercase SQL and so on, there's a connection. So this is how you can tell that this is no longer C, but this is where you plug it with SQL. And then you have these extra comments that surround your C code, plus you put the SQL query right in the middle of the C code, just like that, right? And of course, you have to understand that this is not C anymore, or at least not just C. This is really an extension of C, a syntactic extension of C that allows you to put a SQL query in the middle of it that's going to connect to a database. And what you have to understand here is that what you achieve with that is that you have some C variables, so just like you have Java variables or Python variables, and you kind of connect these C variables with what you have in the SQL query. So basically, if you typed it on Jupyter, you would put an actual table name in there, or some values or whatever, and you connect it with some C variable, right? So this is how you literally embed SQL inside the host language, because SQL is inside the C program. Notice that you don't have any quotes around here. This is literally put in there, and this is something the compiler already sees, right? Here's another example. Again, I'm not expecting you to understand these things. I'm telling you this is just so you see what it looks like to the programmers. This is in, I think, Java. So in Java, you basically have, you recognize some Java keywords here, and then you have this sharp SQL that's no longer Java, it's an extension that allows you to put your SQL query in there, still using this way with the colon to plug whatever is in here, to plug it with some Java variables that are somewhere else. So min and max basically are plugged into Java. And then you have again here some SQL command, fetch we didn't cover. All right, so this is the idea of how you plug the SQL inside your language. And so these sort of things that you see here is basically what you typically will have in here. Basically, when the people who program the application tier, they are going to see code that typically looks like this. Now, I told you there's no quotes around. In that case, you just put it directly inside the code and connect the variables. But there is another approach that is slightly different. And unlike this approach that really modifies the language and adds structures that are not initially part of Java or C, with this approach here, you don't touch Java, you don't touch C. It is totally Java syntax, totally C++, Python. You don't even modify the syntax anymore. What you do instead is that you put the SQL query inside quotes as a string. So that's how you don't modify the language. For whom is that clear? Right? Because for Java, this is just a string, right? Java at that point doesn't care it's SQL. Of course, it has a small drawback, is that when you do that, the string is not known before you run the program. This is basically what's going to happen dynamically in real time. So you cannot optimize as much as you can with this. With this, you can make more optimization because the compiler can already handle that. All right. There is another problem with this approach compared to this approach. It's that this has a cybersecurity risk. Have you ever heard of SQL injection attacks? Right? Imagine, let me just try very quickly to give you an intuition of that. Imagine that this here is what you have on your website, on your application server. And imagine you're building the string where here, this birth here, is taken from what the user put on the website, right? You have on your HTML page some text box, and the user writes something in the text box, and then you concatenate whatever is in the text box with this inside the string, and you do it on the fly. Now, imagine an attacker, a malevolent attacker, who says, oh, this text, what I write in the text box, is just going to be put inside this SQL string on the server, or they might guess that maybe. So what does an attacker do? They basically add some quote or some semicolon to basically force end the statement, and that then starts putting like delete star from blah blah blah, or some SQL query that basically does something bad. And you realize that that wasn't the intent of the programmer here, because the programmer really just wanted to insert a birth here. But it's possible to attack the whole thing by basically putting whatever it takes in the text box on the web page in order to get some SQL code to execute that does something bad, right? So nowadays it's well known that this exists, and there are ways you can mitigate this or avoid these things from happening. Now a lot of people are aware of this, but this is one of the dangers of doing it dynamically as opposed to like this at compile time, where it can not happen. Okay, so this is called the SQL injection attack, right? Yes.
Yeah, I think you just explained SQL. Does it actually still work in this library that you mentioned here? Because most of them, to my knowledge, they deactivate the stacked queries already.
Yes, exactly. Yes, so it is true that nowadays, I mean, this is old, right? The SQL injection attacks. So now there's a lot of measures that are taken by default, but of course, it happens if your people are educated to basically know these things and configure it properly, right? For the smaller businesses, it's a bit more risky. These kind of things can happen a bit more. But the other aspect to it is that it's a perpetual fight between basically the security team of the companies and the outside attackers, right? And it's never ending, right? Because you might deactivate things, but there will always be things you can find to basically circumvent it or attack in different ways, right? Yeah.
I think we need to insert something inside the query, like with the union select or with some blind SQL injection that does some select statement and then returns something or nothing. But I think the stack query attack, which is of course the nicest from the hacker perspective, I think it doesn't work. I was just wondering if this library maybe still has to activate. Because I think in PHP, I don't know about this, but in PHP and Python, I think it doesn't.
So yeah, absolutely. So today, a lot of measures have been taken, and it's not as dangerous as it used to be. But here, it's not a cybersecurity lecture, right? So my goal was to basically just make you aware of what it means to have a SQL injection attack, and the dangers of building strings like that, where you directly concatenate input from the user from the web page. That's the point I want to make. But I totally agree with you that now we have gone a long way, and there's a lot of awareness of these things, and there's a lot of things that get deactivated in order to prevent this, right? But there's just the general rule of thumb that whenever you concatenate things into string, you have to be careful of what you put in there. Yeah. Okay. But again, that's not a cybersecurity lecture, and I'm not even a cybersecurity researcher. So, you know, I don't even have deep knowledge about these things, right? So thank you for your remark. Okay. Now, if you, okay, so this here is to show you more about how it works. So here we have the connection string I told you about. This is typically the name of the database. That's the host you connect to. And here PostgreSQL. And here you put the user and the password as separate properties. Of course, in practice, it's not done like that. You store them somewhere secure and encrypted and so on, and use other protocols. But basically just to show you a skeleton, right? If you put the user and password in there, they can also be, I think that's the next slide, inside the connection string. This we do in exercises, right? Because it's really not important, and the password is not even a secret. So in that case, you just put them in there. Okay. So the connection string really has, in the case of PostgreSQL, the host, the database name, the user, and the password, right? And you specify that to the program, and then it will connect to the PostgreSQL database. Now to show you after doing that, how it's done is that you have two ways. You can either use something called create statements, and then you execute the query with your SQL string, or you put a SQL string inside ahead of time inside something called prepare statement. Then you execute it, but without passing anything anymore. So there's these two ways. Why? It will become obvious in a moment. So if I take this on the left, create statement, then the query, this is what it looks like. You basically create a statement using the connection, and the connection basically is what you created from here. So when you input the URL and got a connection back, then you say execute query, and you put your SQL query as a string in there. And the opposite way, so that one from the right, you put inside prepare statement your secret string, and then you can repeatedly execute the same query over and over and over again, right? So the advantage you get here is that you just pass it once, then you do it multiple times. And once you have done that, when you execute the query, what you need to do is to take the results and process them. So here's an example of how you process the output of a SQL query in an imperative programming language. Very rudimentary, right? So you basically have an iterator. This is what we call volcano iterators in practice. Whoever saw these, like open, has next, next, has next, next, and then close. Whoever saw that? Who never saw that? Okay, so let me explain. So in software engineering, there are a few patterns that people use in order to interact with computer programs. One of the patterns is used when you want to iterate over a very large quantity of whatever. In that case, we want to iterate over a very large quantity of records, right? We have a table. It has maybe thousands of records, or even just 10 records if it's a product search result page. But basically, you want to iterate over the records. In that case, there are three of them, Einstein, Mirzakhani, and Turing, right? In SQL, you don't need to worry about this, because in SQL, a table is a first-class citizen. A table is whatever the SQL query returns, and you just see the table in Jupyter Notebooks, right? You see it on your screen. So when you interact with Jupyter Notebook and get the SQL results, you don't care about iterating. You just put your SQL query, get the table back, and that's it. But the thing is, when you use a language like Java or C++ or Python, you need to actually process it. You need to go through the records and do something with them. In that case, you probably want to build a web page with the results. So you need to go one by one, the first record, the second record, the third record, and for every record, you build HTML codes that will display it on the page. And again, that has to do with the fact that Java, C++, Python are imperative languages. And so what you do in order to iterate is you use, it's an API, let's call it an API, it's a form of interface that has, let me summarize it to two functions, has next and next. Has next tells you yes or no, there is another record left to process, and next gives you the next record. And so basically the way you use an API like that is you call has next, it says yes, so you call next and get the next record. You call has next again, it says yes, so you call next and get the next record. You call has next again, it says yes, you call next, you get the next record. You call has next again, you get no as an answer, then you stop, you're done, right? And so this is what we are doing here, right? We are basically calling has next, it says yes, so we call next, and then when we have the next one, so we are pointing to the first record. And then in my language, I can say get string one. It means I want the first column. So this API works with numbers of columns. So the first column as a string, and that's going to give me Einstein. Then I say the second column as an int here, and that's giving to me 1909, and I store it in some Java variable. And then result.get in 3 from the third column, and I store it in a Java variable. So you see the impedance mismatch, right? Here we have a table with rows and attributes and columns, but in order to make it work in an imperative language, we have to just iterate through it. So next, followed by get string, get int, and then we again do next. There's a has next that I didn't write, but you also have as next that returns true. Then next, and then it's going to be the second one. So get string 1 Miyazakani, get int 2 2014, get int 3 2. Then has next says again through, and you continue, right? So gets every time the string, the int, and the int. And a typical thing you do with that is you build HTML tags, right? That basically correspond to the HTML for the rows of a table, and then you can generate the HTML that displays the table to the user. For whom is that clear? Right? And the reason it's so complicated is really because of this. This is the reason it's complicated. It's the impedance mismatch. We have totally different worlds that don't speak the same vocabulary, the same language, or even view the data in the same way. And that is the reason why we have to deal with that complexity, right? So again, if I summarize here, what you do typically in Java or Python or C++, in a language like that, is you iterate over the records, process them one by one, and then get the values and do something with them, right? All right. Now you can also execute updates. Doesn't have to be select. Can also be insert. But the nice thing is that what you can do is use some special characters to keep some parameters open. Imagine that you have a query that you execute a lot, but with a different age every time. So what you can do is put a question mark in there and then save it as a statement. Then what you can do is you set this to 65, let's say, and then you execute the update. Then you set it to 150, and then you execute the update. So what that means is you reuse that query pattern multiple times, but every time you change the number you put in there. For whom is that clear? Right? So the question mark is really a placeholder, and that allows you, with your Java, Python, C++ language, to use a different value every time. Okay. All right, so this is just more and more code. That would be Python, what it looks like in Python. That would be what it looks like in PHP. Who knows PHP? Right, PHP is one of the older languages for dynamic websites, and typically PHP plus SQL is quite popular, or at least was quite popular at some time. All right, and you see here, it's actually generating HTML, right? This is HTML, these tags that you see in here. Who has ever seen HTML? Who has never seen HTML? You've all seen HTML, perfect. So this is generating HTML. All right. This one is called SQL Alchemy in Python. And this was the point 3 I showed you earlier about data frame APIs. So what happens with that kind of library is that instead of writing a SQL query, either as a string or in the syntax, instead of that, you use an API, a data frame API, like pandas and so on, in that case, SQL Alchemy. And then you recognize some of the words like group by, outer join, and so on. But this is no longer SQL. It's still the relational algebra, still the operators of the relational algebra. But now, instead of being SQL, it's just a function call that bit. So that is typically an API, right? Okay, I'm done throwing ugly code at you. So now you know what it feels like. The main message that I had really here for you is it's complicated, right? There is this impedance mismatch between SQL and the languages, the host languages you use on the application server. And it means that when you plug the two together and make them communicate, it's really, really not easy to do. Okay, who is with me? All right. So now you can set it aside because those were very scary slides. And now I'm continuing with something completely different, which has to do with transactions. Okay. So imagine that I have a database and I'm a bank. And so it's a rudimentary bank. I hope your bank is not implemented in that way, but basically the customer's data is stored in a relational table in some server. And here you have people who are connecting to the table to make updates to the quantities in there. So we have Alice on the left, and we have Bob on the right. So Alice is connecting to the database and issuing some select from where SQL statements, which by now you all understand. And she's asking, well, what's the balance associated with Albert? And the answer is 1,000, exactly, right? This is a selection, name Albert, selects that row, and then select balance, selects this, so it's 1,000. Then Bob does the same thing, select balance from statement name Albert, and gets the result of 1,000, right? Now Alice updates that and sets the balance to 2,000. So what that changes is the value in there, right? Then Bob updates the statement and sets the balance to 3,000. That's updating here, right? Now Alice executes this. So I have two questions. The first question is, what will she see? 3,000, right? What do you think she thought she would see? 2,000, exactly. And this is now we're entering the core of the SQL transaction, because now she actually gets 3,000, and Bob is not surprised, so he gets 3,000, right? Now this is an example with a bank, but you can also think of making reservations on a train, on a plane, you know, when there are multiple people interacting with the system. This is the new thing here. Until now, you were the only person interacting with your database. In practice, there's going to be a lot of people interacting with the database. And the reason is you have a website, you might have thousands or millions of visitors at the same time. They all want to book a ticket or to book a seat in the train. They all want to modify something on their account or send transactions. And so we have to deal with that. And that is one of the benefits of using a relational database management system, is that it knows how to deal with that. And it gives you some very high level control to deal with these things. Now, the core component and what is new is the concept of transaction. What Alice is doing, she doesn't know or doesn't want to know that Bob is also there. Alice wants to execute these three queries, and this group of several queries that belong together, right? They make sense together as a whole, we call a transaction. So Alice wants to execute this transaction. Bob wants to execute this transaction. But you know, they're not supposed to know that they are here. They don't know each other. They're each in front of their machines. And so what happens is that when you think of the high level, what are the desirable properties of a system like PostgreSQL? And there are four of them, four desirable properties. To remember them, we have this Eselsbrücke, ACID, atomicity, consistency, isolation, durability, ACID. Atomicity, not to be confused with the first normal form and atomic values. It means that a transaction, so what you had on the previous slide, two things can happen. Two things. Either all of it gets executed, all of it, or none at all. You might have multiple updates, right, in the same transaction. So it's either or, all or nothing. You cannot have half of the transaction that gets executed. That doesn't exist. So that's the all or nothing. So it's as if the transaction was an inseparable atom, right? All or nothing. Then you have consistency. It means that before and after a transaction, the database must be consistent, right? All the unique, not null, blah, 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 all of these things. Before and after a transaction, the database has to be consistent. Isolation means that Alice and Bob shouldn't even know that they're both there. It should feel like they are the only users of the database. That's called isolation. So PostgreSQL should make you believe that you're the only person interacting with the database. Durability is you do not lose the information. If you update the table and put data in there, then you're assuming it will continue to be there. It's durable, right? The information doesn't get lost. That is durability, right? Here you saw that durability, we had a problem because the 2,000 of Alice in there was completely lost. So here that's a durability issue. There's also a problem with isolation, because here you see Alice is not isolated. She sees the 3,000 that Bob actually put in there at the same time. So you see, this is breaking all of these. But the nice thing is that in the relational database management systems of today, we can actually implement these 4 things and make it so that the users believe that this all holds. So what are the things that can happen? Here, I'm using the same approach as to justify normal forms. When we justified normal forms, I told you, if you have a big table that does everything, you have update anomalies, insertion anomalies, deletion anomalies, right? It's the undesirable things that you see, but you don't want to see. I'm doing the same thing here. What are the things that can happen when too many people access the database at the same time? The first thing that can happen is that Alice sees something that Bob hasn't committed yet. What does commit mean? Commit means the whole transaction has been executed. That's committed. If the transaction was not executed, we say rolled back, right? You either commit, everything is applied, all the changes, or you roll back, meaning forget about it, nothing is applied, right? That's called rolling back. Uncommitted changes means that you are in the middle of Bob's transaction. Some of his SQL updates were executed, but not all of them. It means it's not committed yet, right? The transaction has not been finished. And when somebody else sees data that wasn't committed, the transaction wasn't done, we call it a dirty read, right? And you do not want that. This is bad when it happens, right? It's like you see some booked seats on the plane by other people, even though they haven't actually reserved the seats, right? So that would be a dirty read. Then we have a non-repeatable read. This is also something we don't want. Is that you have a transaction, you're looking at the table, and you read and read again and read again, but every time the data is different. That is weird, right? If you just read the data, it should always be the same, right? But if you have a non-repeatable read, it means that if you do it multiple times, you see that the data has changed. That is a breach in isolation, right? Because you're actually seeing the effects of what other people do. Another phenomenon is a phantom read. When you have a phantom read, the data doesn't actually change. However, you might see new records or deleted records. These are basically extra rows that you find in there. So some people have committed them, and now there's more and more records that you see. This is called a phantom read. This is not to be confused with the non-repeatable read, because here it's the same records that changes, right? But in the phantom read, it's new records that gets added, right? And then there is another phenomenon, which is the serialization anomaly. And to explain that, you really have to think of what is an ideal world. In an ideal world, people take turns, right? It means that Alice, Bob want to do transaction, they just alternate. Alice has the whole database to herself, executes her transaction, commits, she's done. Then Bob arrives, does his transaction, commits, he's done. Then Alice comes, does the transaction. This is called a serializable or serial execution. They take turns, but at no point in time do you have concurrent transactions, right? And what we want to achieve in a system is that even though all of these people are accessing the database at the same time, it should be as if they were actually taking turns. So the database has to give you the illusion that people are actually taking turns, even though for performance reasons, it's actually doing everything at the same time. This is called serializable, serializability. And what we call a serialization anomaly is that you have some transactions, but it's actually not possible to pretend that people are taking turns because of the interactions between them. So that's yet another phenomenon. And that I will get, of course, more in details about. So basically, we'll come back to that example and try to understand with the anomalies that I have given to you, right? So now, if you look at this, the anomaly that you saw here is a dirty read. That's a dirty read because this here wasn't committed yet. Bob will only commit when he's done. So this is not committed yet, but Alice sees it. So that's a dirty read. Who agrees? Right? So this is an anomaly, and we want to avoid that. So in order to think about this whole thing of serialization, we have some algorithms and some approach that tries to think about how we can disentangle all of these things in such a way that we make it work. And so the first thing that we do, of course, we are not going to go as much into the details as for computer science students, but just to give you the intuition, we want to understand the dependencies between the two sides. For example, if I look here, I have a dependency between these two because here she's reading something and he's writing something. So I'm putting in a row here, and what I want to say with that row is the order is important. Do you see that if she reads first and he writes afterwards, it's not the same thing as if he would write first and then she would read? Who agrees with that? So I'm basically adding these arrows saying the order is important, right? If this happens like here, it's really important that this one comes before that one. So this is called a read-write dependency because this is a reading query, select from where. This is a write query because it changes something. That's a read-write dependency. This is also a read-write dependency, right? They are both looking at the same thing. He reads before she writes. So I'm adding this arrow. Read-write dependency or read-write conflict. Then I have write-write dependencies. This is because Alice writes 2000 first and then Bob writes 3000. So I'm putting in a row between the two of a different color that basically says the order is important. Because if you swap, what happens? If Bob writes first and then Alice, then here you would see 2000. So you see, it actually matters what the order is. So this is why we put an arrow in here to say, be careful. Here, that's a write-write conflict. And finally, we have write-read conflicts when first a write and then a read. And here you have one here where this writes first and then this reads. And of course, it's important because if it was read first, you would have 2000 and not 3000. And here too, you have a write-read conflict where the order is also important. Who is with me? All right, so that's the first thing we do when you have transactions like that, we put the arrows in here. And then we abstract away and look at the graph. And so basically, and that's what we do typically in textbook exercises, instead of looking at the specific queries, we don't care actually what is in the query. What we care about is that Alice read the Albert Einstein record. Bob reads the Albert Einstein record. Alice writes the Albert Einstein record. Bob writes the Albert Einstein record. And I'm just looking top down. This, from top to bottom, right? And this is called the schedule. All right, who is with me? Right. And so typically, if I give you a schedule like that, you have to be able to draw it like this and put the arrows in there, right? So next week, I'm going to take it from here, and I'm going to tell you, based on the arrows in here, whether or not you can pretend that they are taking turn, right? Where you can disentangle the spaghetti and have Alice before Bob or Bob before Alice, right? So I'm stopping here for this week, and we'll take it over next week with this with transactions and serializability. So thank you very much, everybody, for attending today. Enjoy the exercises that the TA team prepared for you. And I will see you next week for the continuation of transactions and serializability. Thank you very much.